We're going to start with a demo. You don't have to write this down. You can if you want, where it's just kind of there as an introduction. I might scribble a couple things, but for the most part, what was the difference quotient from advanced functions that look like this? The limit as x approaches a of f at x minus f at a over x minus a. And I showed a demo. If you weren't in my class or if you missed that day, you might have missed the demo, but I showed a demo. We're going to look at it again and talk about it, and then we're going to change a little bit, talk about it again, and start something new. And today we're talking about derivatives, which is kind of a big deal. So our next unit is called derivatives. And basically all the rest of the course that's about calculus is about derivatives. And today we're talking about derivative for the first time. So kind of a big, important moment. Today and tomorrow we're talking about more of the same. So today and tomorrow, you want to understand what's coming on. Here's our demo. This is 1 point. This is the x, where the x value is a. And we said the limit, as you can still see over here, as x approaches a. So as I drag this point across, I can see that x, which is like 1x value, is approaching a. And the reason we did this is when I start here, what do I have? I have a secant. And if I find the slope of a secant, what am I finding? I'm finding the average rate of change between those 2 points. And that's all well and good, in particular from grade 9, when you have 2 points. You're finding the slope of a secant, which is the average rate of change between those 2 points. And that's useful in lots of circumstances. You might want to know what was your average speed on your way to school this morning, because roads weren't very good. And so, sometimes you were going fast, sometimes you were going slow, you got caught at stoplights or whatever, but you got here. How far is it? How long did it take? And that's your average speed to get here, right? And that might be all you care about. But then we noticed that wouldn't it be useful, wouldn't it be interesting to also be able to calculate instantaneous rates of change? So not the rate of change between 2 points, but the rate of change at a particular point. Like right now, this instant, how fast am I moving? Speed is a really easy rate to think about, but of course, this could apply to any rates. Speed's just an easy one for us to think of. The average distance over time is your average speed. At this instant, what distance am I covering in what time? What's my instantaneous speed, rate of change? That's the slope of a tangent. And that's what we did a lot of in the last unit of MHF. And the slope of a tangent looks like, and the reason why it doesn't work is because our formula from grade 9, which is y2 minus y1 over x2 minus x1, which again is like slope of a secant. You put 2 points in, you get the slope, the rate of change between them, you get that out. That's great until I get a tangent, because a tangent by definition is a slope, is a line that touches a curve at a single point. And if you only have 1 point, then your y2 minus y1 over x2 minus x1 doesn't work, because you would end up with something like 3 minus 3 over 2 minus 2, 0 over 0. And at the time when we first learned about that, we didn't have a word for that. We didn't know that was called indeterminate. But we talked about how it could be thought of as a hole in a function and how that's useful. And we could use this idea of limits to get around this. And so what's interesting is we said, if x equals a, we're in trouble, because I get 0 over 0. So what if I just say x is approaching a? X is getting closer and closer and closer. It's not a. It's not a, because we'd be in a lot of trouble. We're just going to get really, really, really close. Okay? And then we do this trickery algebra kind of thing, and we get rid of the hole. And then we can use what's left to calculate the slope of the tangent at that point. So I hope you remember at least some of that. It wasn't that long ago. But the visual can be important to make sense of all this and why it works. So that's what we did in functions, and that was the demo that we used. What if I change the demo a little bit and I change it to this. So I still have A, one of the points, but instead I talk about a distance between my 2 points, which makes my first x value A and my second x value A plus h. And it's just another x value. So you can think of this as the x value, and the x value is approaching A, same idea. And to give you a specific example, if this helps, if this scale is counting by ones, then this x value is 1. H is 1, 2, 3, 4, 5. So A plus H would be 6. So one x value is 1, one x value is 6. We're talking generalities here, but you could think of it that way. And H would be 5. Does that make sense? H is the distance between the 2 x values. And what we're doing is we're doing the same thing where this point approaches this point. So it's a secant, but what if it was turning into a tangent? How would my limit statement change if I wanted to write it for this visual or this demonstration? Think about what our limit statement was. What would it be for this one? As h approaches 0. Very nice. So look, as h is approaching 0, isn't my one x point approaching the other x point? And it will eventually be indeterminate. Do you see that? So now this is the limit as h approaches 0. So this is the limit as h approaches 0. One of my points, okay, was A and F at A. And my other point is A plus H. That's the x value. So what's the y value? F at A plus H. And we're doing the same thing. Y2 minus y1 over x2 minus x1. Like it's exactly the same thing, but we know it's going to be indeterminate, so we need to use our limit notation. And it becomes y2, which is f at A plus H, minus y1, which is f at A, over x2, which is A plus H, minus x1, which is A. How can I simplify this? Yeah, the a's cancel on the bottom. A minus A is 0. And then to complicate matters even further, we often don't use A, we often use X, so I'm just going to rewrite this one more time. And the only reason, actually I'm not going to say equals, I'm going to say or. And I'm only doing this because we usually use X. The variable obviously doesn't matter, but normally that's how you're going to see it. And we have a new formula. And I can only imagine that some of you, many of you, maybe most of you, are going to ask, why are we doing this? What was wrong with the other one? Can this one do something that the other one can't? And my thinking is no. But what I will tell you is beyond high school, I don't think you would ever see the other version. So if you took a calculus course, and I think many of you will, even if you don't go to math, there's usually calculus for other areas. If you would see the H version. So you really need this one, not the other one. Okay? I suppose it's good to have both. There are certain circumstances where the other one the algebra is a little bit easier. There are certain circumstances where this one, the algebra is a little bit easier. But what I'm saying is, this is really the like more common version of this. So don't ask why did we change it? What's different about it? Not really anything is different. The algebra is different, but it was like we used the other one in MHF because we weren't doing derivatives and stuff. This is really the true version, as far as I am concerned, of how this stuff works. And this is called the definition of the derivative. And as I said, that's what the next unit's called, and that's basically what calculus is all about, at least in high school. And so kind of a big deal that this is a definition of a derivative. Sometimes it's called y with a little apostrophe, which is actually called y prime, or f prime at x. Obviously, depending on if you're given an equation in terms of y, then you're using y prime. And we'll get into all of this more really next unit. But if you're given it as y, it's y prime. If you're given it as x, it's f prime. And there's another notation which is dy by dx. And it's really useful in a variety, but one particular that we will look at in this course type of question. It's a really useful notation. Less useful for some other things, but anyway. That's the way it works. So these all mean the same thing. If you're asked to find y prime, if you're asked to find f prime, if you're asked to find dy by dx, sort of depends on the context of the question, sort of depends on how you're given the question, just how it's worded. It really all means the same thing: find the derivative. And you'll get very used to that. That will not probably be a problem for anyone. Any questions on this so far? We're spending 2 days on this. There's a really important aspect to this, but I don't think we'll get to it today, but we'll talk about it a lot tomorrow. It's big. So you're going to notice that this is a very familiar question from last unit, but we're going to use the new version of the formula, so the algebra will look a little bit different, and that may be when you'll ask, why are we complicating things? X minus a was perfectly fine. But if we were going to pick one to do, it would be this one. And we wouldn't do x minus a in MHF. We'd do this instead. Okay, so I'm just rewriting a couple things here, not for any particular reason, just to sort of organize my note and my thinking. F at x equals x squared minus 4x. And in last semester, you might have been given the point, or you might have just been given the x value. Find the slope of the tangent of the curve at x equals a, and you would go and find the y value, right? You do that and say, well, f at 6 equals 12. That's all we're given. So all of this is the same as MHF? Absolutely. So now we have a new formula, though. We never called it f prime at x before, but we're going to start calling it f prime at x now. And this is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. And in this case, we're asked to find the slope of the tangent at a point. So this is actually f prime at 6. And what do? I sub 6 in for all the x's. So this becomes f at 6 plus h minus f at 6 over h. This is maybe the part where it gets a little bit trickier. Some people get a little bit confused. Like, what does f at 6 plus h mean? Well, it means f, which is x squared minus 4x. But I sub this in for all the x's. So f at 6 plus h is this expression, which was x squared minus 4x. Okay? So this is 6 plus h squared minus 4 times 6 plus h minus f at 6, which is 12. Is everybody okay with how we set this up? Because now it just becomes some algebra to make everything work out. But remember, all this comes from that demo, and we just change the values. And people don't like change. That's true in life. People are terrified of change. Everything was fine. Why did you just change it to h instead of x? Like, I don't understand. Again, don't spend too much time worrying about that. I mean, it's just kind of the way it is. There's two different notations, two different ways of looking at it. It's good to know both. This one's actually the one that's more important. But you got to know how to set it up to this point. Okay, and then the part that's different is this next work expanding and simplifying. So I'm expanding this first bracket. What is 6 plus h all squared? It's 36 plus 12h plus h squared. I mean, if you need to take a couple of steps to actually do the expansion, by all means, go for it. But, you know, the more you can kind of use patterns in the formulas that we've learned since grade 10 to do this, the better off you'll be. Everybody okay with that? First binomial squared. Minus 4 times 6 is 24. Minus 4h. And then minus 12 over h. Just looking at my constants, I get 36, I get minus 24, and I get minus 12. What does that work out to? 0, thank you. So in other words, this and this and this are all gone. And I'll simplify anything else, but I don't think in this. Oh, yeah, there is actually. So I've got h squared, and I've got 12h minus 4h left, so that's plus 8h over h. What happened here that's important? Brad. And why is that important? Just like before, you had to get an x minus a factor come out because we had x minus a on the bottom. But in this case, we only have h. So the top will always have a common factor of h, like always. If it doesn't, it's like, oh, maybe this one's different. Okay, I'll move on. No. It's not going to work, right? So we notice that this thing over here must happen. The numerator in this last step, common factors in h, and that's our indeterminate part. And h always approaches 0, so that's all. Like, it's always going to work out the same way. Maybe that's a benefit of this one is this part from here on is pretty straightforward. So I get h times h plus 8 over h, which equals the limit as h approaches 0. Remember what I said before, like h divided by h, those are gone. That's got to be the indeterminate part, which it's just 0 over 0, so it is. So it's, it's simple. Now I can sub 0 in for h equals 8. What does that mean? Yeah, the slope of the tangent at 6 is 8. That's what we were finding in that question, right? We get lost in the algebra, forget what we're actually doing or what we're actually finding. It's always good to kind of go back and think about that. Any questions? Looks like we're working on the same function here, but now we're supposed to find the general derivative. What does that mean? Yeah, what do you think? Yeah, exactly. So not at a particular point like 6, but just generally. And again, this is kind of a big deal. Now here's the rule. Just this is only really applies for like the next 2 days until the test kind of thing, because the next unit things will change and you'll have to wait and see what I mean by that. But when we ask you to find the general derivative, we are requiring you to use this new formula. If you are asked to just find the slope of the tangent at a point, you can use, and that may or may not be on the test, but you can use either formula. You can go back and use the x minus a from MHF if you prefer. Okay? Some of you will prefer, some of you will be fine with this one. It's up to you. But if you're asked to find the general derivative, we mean using the new h formula. All right, so f prime at x equals the limit as h approaches 0. Again, I'm just going to write down the formula. Now I can imagine that this is where some people start to get a little bit like weirded out or confused, because we're subbing x in for x. And that's just an abstract idea. It's something you've seen before, but you want to make sure you understand what's going on and what and exactly how this stuff is working out. So I'm going to color code it here so that we can see. So what is f at x plus h? Remember, I take function notation just tells me I take this and I sub it in for x. So x squared minus 4 times x, but I'm putting x plus h in for x. And like I said, it's weird to sub x in for x, but that's the way this works. Minus, what is f at x? That's just the original function. Is that okay? Now we're just going to do some work to simplify, see how this works out. So x plus h all squared is x squared plus 2xh plus h squared minus 4x minus 4h minus x squared plus 4x. Again, something really important happens here. Is everybody okay? Is everybody caught up all right? Something really important happens here. X squared minus x squared. 4x, hey, what's going on here? 4x minus 4x So I've got h squared plus 2xh minus 4h all over h. Why is this important? Yeah, every term has an h in it, so h can be factored out. And again, that's got to happen. And this is the general derivative for this function, 2x minus 4. And again, when we say find the general derivative, you've got to do it this way with the h formula. If we go back and we look and we see, if the question was worded this way, in the future, you could use x minus a if you wanted. Example 1, find the slope of the tangent at a point. Use either. Okay? But for this one, you have to use the h formula. Now this is really simple. It just says find f prime at 4, f prime at 0, f prime at 2. Again, f prime at x is 2x minus 4. So f prime at 4 is 2 times 4 minus 4, which is 8 minus 4, which is 4. F prime at 0 is 2 times 0 minus 4, which is negative 4. And f prime at 2, 4 minus 4 is 0. Does this paint a picture to anybody what those three values? Does that create a visual at all? What's happening here? What are these values? What is this saying? Yeah, good. It's the slope of the tangent at each of the points. So what? Anybody? Any ideas? Something really important happening here. This said at 4, the slope of the tangent is 4. Positive 4. At 0, the slope of the tangent is negative 4. So wherever it actually touches the tangent, it's going to be negative. And at f at 2, it's 0. What does that mean? What does the slope of 0 mean? It's a horizontal line. Very good. What kind of a curve is causing this to happen? Crude diagram, these should be like points of tangency, but yeah, a parabola. Isn't it a parabola? It sure is. These values are informing us about the parabola in a really important way. Okay, we're going to try a couple more. So we see some of the different types of questions and how the algebra plays out. Sort of look at some of the different notations, I suppose. Because this one says, so notice how this one says, for y equals square root of x plus 4, find dy by dx. It's just a different notation. It's saying the same thing. So what is f at x plus h? I mean, there is no f, but we still use this notation for the formula. So I'm just going to say, if this were f at x, then f at x plus h would be the square root of, instead of x, it's x plus h plus 4, right? Again, this is where it can be confusing, I know, for some people that we're subbing x in for x. So this is the square root of x plus h plus 4 minus the square root of x plus 4 over h. What do you think we're going to do here? Very nice. Which is going to be x plus h plus 4 plus square root of x plus 4 over itself. So the conjugate is going to work like this. First two square root brackets will cancel. And it's going to be minus, be careful, bracket, the second two square roots. And look at this, be careful of this. Don't forget this part at the bottom, it's kind of important. Easy thing to forget is this part that belongs on the bottom. Now, is it easy to see that this is what's going to happen here? This is x minus x and 4 minus 4. We don't probably have to write that step out. The bottom is kind of a pain to write out, so I'm going to try to skip it. Otherwise, it's like, ugh. So x minus x is gone, 4 minus 4 is gone. I just get h over h times this whole thing. And look at that. It's already factored for us. 1 over subbing 0 in. And I get x plus 0 plus 4 is just x plus 4. So this simplifies to, make sure you understand this, 2 root x plus 4. I'm adding them, not multiplying them, so be careful of that. 2 root x plus 4. Done. Kind of interesting to see how, like, we get this whole big mess of conjugates and stuff. Like, it looks really big and it simplifies to something so nice. And is that okay, everybody? This next part is kind of trivial, but remember what we're finding. There's one thing about it that we need to know. So this was 1 over 2 root x plus 4. This is where this notation, at least to me, dy by dx, is not useful for when we're subbing in points. There's no nice way of doing it. There isn't really for with a y either. That's why function notation is so nice. So you could just say, dy by dx at a point, but sometimes you'll see we use like a diagonal line when x equals -3. Not very elegant. So 1 over 2 root negative 3 plus 4, which is square root of 1, so 1 over 2 times 1, which is 1 over 2. Square root of 9 is 3. 2 times 3, 6. Any questions about that? We're going to do one more. So again, this one says find the general derivative and then the slope of the tangent when x equals 2. So we've got to use the new formula. It's kind of the point of today anyway, so we would today anyway. But we saw just a polynomial function. We saw square root. And now we're looking at a rational. And the rational one is pretty straightforward. It's not really different. It's not really trickier than the other two. Your intuition of what you would do will be correct. So.
If the tangent equals 1, is that a square root graph always?
No. What do you mean if the tangent equals 1?
Like, if we get like, let's say like x at 0, and the tangent equals, like the slope is 1.
I see what you're saying. Of the regular square root function, that would be true, but not necessarily of all square root functions. So no, you could have any graph, like any kind of function, sine function, anything, where if you do transformations in the right way, you'd get a particular tangent in a particular location. You know what I mean? By just doing like shifts. Yeah. Okay, so let's take a look at this. F prime at x is the limit as h approaches 0. F at x plus h minus f at x all over h. So what's f at x plus h? It's 1 over x plus h plus 2 minus f at x, which is 1 over x plus 2 all over h. And here we're going to do common denominator. And I don't think you need my help for this. You can just go ahead and do it. Again, maybe I'll sort of, it's not really skipping a step, but just like for the lesson, I would normally write this out. But like distributing this negative means you're going to get x minus x and 2 minus 2. Right? So those are gone. Just be careful. You get negative h as well. So see if you can finish this one on your own. Yeah. No, you have to find the general derivative first. So you got to simplify that expression fully to meet these instructions because it said find the general derivative first. So we saw the h's canceling out. I get this, right? And then sub-zero in, and this is just x plus 2 times x plus 2, so it's x plus 2 all squared, and there's the general derivative. And then at x equals 2, sub 2 in, 2 plus 2 is 4, 4 squared 16, negative 1 over 16. Any questions? Okay, the worksheet that was posted, it says in the classroom, but you're only doing a few of the questions to start. Same worksheet for the practice for tomorrow. We're going to do another day on this, talk about something where we don't have enough time to get into it. So we'll leave it for tomorrow, but talk about something really important in terms of the idea of derivatives, something about them. But that will be tomorrow.